Hi everyone, and welcome to my talk, which is titled One Bit to Rule Them All, Binarizing Reconstruction in One Bit Compressive Sensing. My name is Thomas Feuillen, and this is a joint work with Mike Davies from the University of Edinburgh, Luc Vandendorpe and Laurent Jacques from the University of UC Louvain in Belgium. So a quick overview of the talk. So in the first part we're going to see what you can do when you want to quantize your measurement. So for example, when you want to lower the resolution of your ADCs. In the second part, we're going to study what happens when you also want to lower the resolution of your reconstruction. So let's look first at the quantized measurement. Here, consider that you've got a linear model that links your measurement to what you want to recover. For example, in the context of radar signal processing, a range profile where you want to recover these two guys, the position of these two guys, and the measurement and your vector are linked by a measurement matrix for, again, in the context of radar signal processing, is a Fourier transform. Okay, now if you have too much data that you need to sample and you want to lower the amount of data, one way is to use compressive sensing to subsample those measurements, and you can do that if this vector is sparse, so if there's not too many targets that you want to recover, and if this matrix has the RIP, so the restricted isometry property, which simply says that those elements in the matrix are roughly orthogonal with each other. So you can lower the number of measurements. But another way of lowering the amount of data that you need could be to lower their resolution. So now each of these measurements have a lower resolution. But this begs a question. Given the different types of quantizer that you can use, you can wonder which quantizer you should use to do that efficiently. So in this talk, what we're going to study is the simplest, which is the one-bit quantizer that you apply in the real and in the imaginary domain. So effectively, you just keep the quadrant in which the signal is lying. Okay? But given this really sharp loss of resolution and information, you can ask yourself, is there going to be scenarios where the measurements that you get are a bit ambiguous? And what I mean by that is cases where you have, for example, two different sparse vectors that once projected and then quantized give you exactly the same bits. So when you get a measurement, you don't know if what you're seeing is actually this guy or this one. And this, in the context of Fourier transform, can happen quite easily. For example, if you have a one sparse vector here, which, because it's a Fourier transform, will be a phasor turning in the complex plane. So that's your first sparse vector, and then you have a two sparse vector, which is the same one plus a smaller component rotating around it. And if you have that, you see that, for example, for different measurement, they always lie exactly in the same quadrant. Okay? And this is a big issue, because it means that when you get those measurements, you don't know if it was this vector or this one. And this puts a severe bound on your reconstruction. Is there a way to overcome this problem? You see that the main issue that we have is that even if we get an infinite amount of measurement, we essentially get always the same bits. So there's no gain of information. But if we were to change the threshold randomly, okay, for each measurement, there might be a way for us to get more information. And this is called a dither, so changing those thresholds by adding this component. And this dithering, if it follows, in our context, a uniform distribution that spans the dynamic of your signal, you will be able to get something a bit more interesting. And just to give you a quick insight, you can already see that if you take the expected value of your one-bit dithered measurement, okay, because of this dithering, those measurements go back to the full resolution data. So that's one way of seeing the advantage of doing that. So we've got the model and we've got the quantizer. So let's look now at ways of processing the data. So here, again, I'm just going to review the simple algorithm that one can use, which is the projected back projection, which simply said is just a match filter that you apply on your quantized measurement, and then you pick the k-best element out of that. So because it's so simple, it comes with lots of pros and cons, so let's just go through it. So first one, super simple, everyone can implement that. So simple actually that if you look at it, you don't really use explicitly the dithering that was used, okay? In the sense that it is applied to those measurements, but you don't really see it here in the equation. And it means that if you were to implement it in hardware, it means that you just need to generate the dithering and apply it to the measurement, but you don't need to control it or to measure it to use it in the reconstruction itself. The last big advantage is that this algorithm is one of the few that has a uniform reconstruction for all vectors. Okay, so before there was a situation where you could not really know what was happening, but here, for any sparse vector, the reconstruction will behave like this. So which means that if you want to have a better estimate, you just need to increase your number of measurements. And this is a big difference with what we had before. But of course, this algorithm is so simple that it could not be the best. And for example, in cases where you have a low number of measurements, there's no magic in the sense that because we're not using explicitly the dither, there's no way also for the algorithm to know what is due from the signal and what is coming from the dither. And so in cases when there's not too many measurements and lots of targets to recover, the signal is in a sense lost in the dither, okay? Because you need to remember what is happening is that we get a signal, we add a random dithering to it, which is as big as your signal, so you've got an SNR of 0, and then you quantize it. So for low number of measurement, there's no magic, you might not get the best performances. Other algorithm exists that gives you better performances, but we don't have time to review it here. So that was all for what happens when you want to quantize your measurement. Now, if you want to go even further to quantize your reconstruction, let's see what happens. Because if you think about it, what we're doing up to now is just looking at the acquisition part, but we're not doing anything about the reconstruction. And so for the acquisition, because this is a lower resolution, we have a gain, so we can use lower resolution ADCs, low power, or maybe higher frequencies, but we're not doing anything smart here. And, and actually, if you look, we are processing those 1-bit measurements in the same way as we would process high resolution data. So we could try to do something a bit different, which is to also lower the resolution of this back projection operator. What would you want to do that? If you were to do that, all of your computation will just be then between 1-bit measurement and a 1-bit back projection, which could help you to get more efficient processing because it's just 1-bit computations. And this could help you in situation when you want to have either a really low cost or low power application, or when you have lots of different sensors, and so too much data and too much power. But again, lowering this resolution would come at a cost. And now in the rest of the talk, we're going to study what happens in terms of the reconstruction performances and what can you get in terms of guarantees, okay, on what we're doing. So this is what we're proposing. So we change this high resolution back projection to its 1-bit and dithered equivalent. So now we've got 1 bit for the measurement, 1 bit for the back projection, so we have 1 bit to rule them all. Hence the title of the talk. So let's look now at what happens for the L2 reconstruction. So for the quality of your reconstruction, when you compare your estimate with the ground truth. This is what you have. So your 1-bit measurement and your 1-bit back projection. The first thing that one can do is to come back to what you already know, which is what happens when you have a high resolution back projection on quantized data. So this is the BBP algorithm that we've seen. And this, we know its behavior. We know how it will scale. It will scale as square root of k over m. And now the last thing that we need to do is to upper bound this term, which is like a discrepancy between your high resolution processing and your low resolution processing, okay? So, okay, let's look at this term. What can we say about it? Maybe a first guess would be to consider that as a noise, okay? That in a noise term. But looking at the structure of the equation, we see that if this is a noise, we effectively have a multiplicative noise because it's been multiplied by your measurement. This assumption gives you a really bad bound, because if you look at this bound, it doesn't depend on m, so on the number of measurement, which means that no matter the number of measurement, you will get a bad estimate. So that is not the way to go. We need to find another way of doing it. Another way would be to leverage the dithering, because here we know from the structure of a quantizer that this guy on average or in expectation, will go back to this high resolution processing. Leveraging that allows us to use concentration of measure inequalities like Hoeffding, which can help us to get a tighter estimate. So if you do that, after a bit of work and sweat and tears, this is what you get. So I won't bore you with the whole theorem, but basically it says that if your matrix has the RIP, and if you have a k-sparse vector and you use it with the quantized operator that we've been defining, these discrepancy terms can be scaled by that with some probability. Furthermore, there's some condition that you have to impose on m, which should be bigger than that. But if you look at that, it also means that if you inverse this relationship, gamma, which is also here, will scale as 1 over square root of m. So if you put everything together, with the previous bound on the back projection on quantized data, you get that. And what does it mean, this? It means that the quantized back projection on quantized data behave exactly as the high resolution back projection on quantized data, so with square root of k over m, just with a bigger constant in front of it. And this is exactly what we see here in the simulation. So the red dashed curve is for where you have two non-zero components, and this is the curve for a high resolution back projection on quantized data. And here we're looking at the L2 reconstruction for different number of measurements in log terms. Okay, so this curve, you see that it scales as 1 over square root of m, as expected, but now when you compare it to the solid curve, which is the quantized back projection on quantized data, it is exactly the same, but just slightly shifted to the right. Which means that if you want to make up for the loss of resolution in the processing, you just need to slightly increase your measurement, which is quite interesting. And again, if you increase the number of targets to recover, then you need more measurement. I could leave you with that, but we could also try to go even further. You see, if we look at what we're doing, we've been applying this back projection as a matrix multiplication with this complexity, but we know that working with Fourier transform, for example, that back projection can be computed more efficiently in some cases. For example, for the Fourier transform, as I've said, you can have this complexity because you can access a factorized model of your back projection with fewer components. And the question that we're asking now is, can we leverage both the low resolution of our processing and the low complexity of the underlying factorized model? And the short answer to that is yes, and I'm working on finishing the draft as we speak, so the paper will be coming soon. But while we wait for me to finish the draft, let's have a sneak peek of the performances that we can get. Here, the red curve is what we had before, so it is the quantized back projection on quantized data when you apply it as a matrix multiplication. And this is, so for a Fourier transform, the QFFT. So the quantization on each element of the factorizable model. Again, we see the same type of behavior, so it decreases as 1 over square root of m. But interestingly, you see that also you need more measurement for it to work. But this graph, in a sense, is a bit unfair because we're comparing it in terms of number of measurement, not complexity. So if we were to change this axis, in a sense, this curve, because it has a lower complexity than this one, might be much more appealing. So this is the end of my talk. So what we've seen is that you can get uniform recovery guarantees for any RIP matrix when you want to do the quantized back projection of quantized data with sparse vectors. We see that considering the loss of resolution in the processing, we suffer from relatively low losses in terms of performances. You just need to slightly increase the number of measurements to make up for it. Also here, I didn't show it here in the talk because I like the title of 1 bit to rule them all, but your measurement do not need to be quantized for it to work. You can do it with classic high resolution measurement. We've also seen that the dithering is necessary if you want to make it work. And in the end, we've seen that we can leverage both the low complexity and the low resolution if you use a factorizable model to have something that looks like a QFFT. So this is the end of the talk. If you've got any question, I'd be more than happy to answer them. If you want to contact me, this is my email, my website when the slides will be available of the talk, and this is my Twitter handle. And I just want to finish with some non-exhaustive references. So thank you.